a place in my beautiful balloon. It wears a nicer face in my beautiful balloon. We can sing songs along the silver sky, or we can fly. We can fly up, up and away. My beautiful balloon. Suspended under the twilight canopy, we'll search the clouds for a star to guide us. If by some chance you find yourself loving me, we'll find a cloud that hides us. We'll keep the moon beside us. Love is waiting there in my beautiful balloon. Way up in the air in my beautiful balloon. If you hold my hand, we'll chase your dream across the sky. For we can fly, we can fly up, up and away. My beautiful balloon. Hey, up, up and away. My beautiful balloon. Yes, you. Hey, I'm saying all the things that I know you like, making good conversation. I gotta handle you just right. You know what I mean. I took you to an intimate restaurant, then to a suggestive movie. There's nothing left to talk about unless it's horizontally. Let's get physical, physical. I wanna get physical. Let's get it physical. Let me hear your body talk. Let me hear your body talk. Let's get physical, physical. I wanna get physical. Let's get it physical. Let me hear your body talk. Let me hear your body talk. I've been patient, I've been good. Try to keep my hands on the table. It's getting hard, this holding back. You know what I mean. I'm sure you'll understand my point of view. We know each other mentally. You gotta know that you're bringing out the animal in me. Let's get physical, physical. I wanna get physical. Let's get it physical. Let me hear your body talk. Let me hear your body talk. Let's get physical, physical. I wanna get physical. Let's get it physical. Let me hear your body Let's get physical, physical. I wanna get physical. Let's get into physical. Let me hear your body talk, your body talk. Let me hear your body talk. Let's get animal, animal. I wanna get animal. Let's get into animal. Let me hear your body talk. Let me hear your body talk. Ain't no mountain high, ain't no valley low, ain't no river wide enough, baby. If you need me, call me. No matter where you are, no matter how far. Just call my name, I'll be there in a hurry. You don't have to worry, 'cause baby, there ain't no mountain high enough, ain't no valley low enough, ain't no river wide enough to keep me from getting to you. Remember the day I set you free? I told you you could always count on me, girl. And from that day on, I made a vow I'll be there when you want me somewhere. 'Cause baby, there ain't no mountain high enough, ain't no valley low enough, ain't no river wide enough to keep me from getting to you. No wind, no rain, or winter's cold can stop me, baby. 'Cause you are if you ever in trouble, I'll be there on the double. Just send for me, oh baby. My love is alive, way down in my heart. Although we are miles apart, and if you ever need a helping hand, I'll be there on the double, just as fast as I can. You know that there ain't no mountain high enough, ain't no valley low enough, ain't no river wide enough to keep me from getting to you. 'Cause baby, there ain't no mountain high enough, ain't no valley low enough, ain't no river wide enough to keep me from getting to you.
Young teacher, the subject of schoolgirl fantasy. She wants him so badly, knows what she wants to be. Inside her there's longing, this girl's an open page, bookmarking, she's so close now, this girl is half his age. Don't stand so close to me. Don't stand so close to me. Her friends are so jealous, you know how bad girls get. Sometimes it's not so easy to be the teacher's pet. Temptation frustration so bad it makes him cry. Wet bus stop, she's waiting. His car is warm and dry. Don't stand so close to me. Don't stand so close to me. Talk in the classroom, to her they try and try. Strong words in the staff room, the accusations lie. It's no use, he sees her, he starts to shake and cough, just like the old man in that book by Nabokov. Don't stand so close to me. Don't stand so close to me. Don't stand so close to me. Oh, don't stand so close to me. Don't stand so close to me. Please don't stand so close to me. Please don't stand so close to me. Don't stand so close to me.
Would you like to ride in my beautiful balloon? Would you like to ride in my beautiful balloon? We could float among the stars together, you and I. For we can fly, up and away, my beautiful balloon. The world's a nicer place in my beautiful balloon. It wears a nicer face in my beautiful balloon. We can sing a song and sail along the silver sky. But we can fly, up and away, my beautiful balloon. Suspended under the twilight canopy, we'll search the clouds for a star to guide us. If by some chance you find yourself loving me, we'll find a cloud that hides us. We'll keep the moon beside us. Love is waiting there in my beautiful balloon. Way up in the air in my beautiful balloon. If you hold my hand, we'll chase your dream across the just right. You know what I mean. I took you to an intimate restaurant, then to a suggestive movie. There's nothing left to talk about unless it's horizontally. Let's get physical, physical. I wanna get physical. Let's get it physical. Let me hear your body talk. Let me hear your body talk. Let's get physical, physical. I wanna get physical. Let's get it physical. Let me hear your body talk. Let me hear your body talk. I've been patient, I've been good. Try to keep my hands on the table. It's getting hard, this holding back. You know what I mean. I'm sure you'll understand my point of view. We know each other mentally. You gotta know that you're bringing out the animal in me. Let's get physical, physical. I wanna...
Buenos días a todos los asistentes, presencialmente y por videoconferencia. Nos reunimos hoy para dar entrada al nuevo académico correspondiente. En los estatutos y en el reglamento de régimen interior de la Real Academia de Ingeniería de España se contempla la figura de académicos y académicas correspondientes que serán elegidos y nombrados entre personalidades no residentes en España, que se hayan hecho acreedoras a tal distinción por méritos análogos a los requeridos para ocupar plaza de académico de número. Quiero decir que esto se lo he contado antes al profesor en inglés, pero oficialmente, por ser un acto oficial de la Academia, lo hacemos en español, pero ya lo sabe él lo que le estoy diciendo. Se requiere una cualificación relevante, además de una reconocida integridad profesional, así como reunir algunas de las condiciones siguientes. Haber realizado aportaciones de destacada importancia en materias teóricas o aplicadas vinculadas a la ingeniería, que estén reflejadas en patentes o publicaciones de pertinente nivel. Haber demostrado excepcional competencia para lograr avances significativos en nuevos campos tecnológicos o en su desarrollo empresarial. También constituirán méritos para la incorporación a la Academia el haberse mostrado eficaz en la dirección de empresas e instituciones, poniendo de manifiesto capacidad para afrontar y resolver problemas nuevos o complejos y contribuir a la innovación, así como haber prestado servicios relevantes para la docencia y formación de ingenieros. Tiene la palabra el secretario general de la Real Academia de Ingeniería de España, el excelentísimo señor don Jaime Domínguez Abascal.
Buenas tardes. Bueno, en sesión plenaria de la Real Academia de Ingeniería, celebrada el 19 de noviembre de 2019, fue elegido académico correspondiente el profesor JN Reddy. Tiene la palabra el profesor Dollaré.
Well, good morning, everybody. First, in Spanish, just one single sentence. Señor presidente, señoras y señores académicos, señoras y señores todos presentes, Professor Reddy, I'm going to move to English. Well, it's for me a pleasure and a privilege to impart this laudation in honor of Professor Dr. JN Reddy as part of the ceremony of his entrance as corresponding member of the Spanish Royal Academy of Engineering. I'd like to start thanking Professor Reddy for accepting the invitation of our Academy that was initially proposed by the academicians Jaime Dominguez, Jose Dominguez, Francisco Herrera, and me, and was approved unanimously in the plenary session of the Academia held on November 19 in 2019, just before the terrible pandemic that we suffered, and that delayed this event much longer than we had liked. Fortunately, we are here to welcome one of the most brilliant engineers of our generation, recognized worldwide for his fundamental contributions in computational mechanics and material science. Dr. Reddy is not only an extraordinary scientist, but one of those rare examples that combines in a single person the complete cycle of successful research, from generation of basic knowledge to its transfer to new engineers and scientists and to the research community and industry, who has employed it to make cheaper and safer materials and structural components. Professor Reddy was born in Warangal, in India, in 1945. He graduated in mechanical engineering at Tasmania University, also in India, and obtained a doctorate degree from the University of Alabama in Huntsville in 1974, under the supervision of Professor J. Tinsley Oden, one of the fathers of modern computational mechanics. After two short periods as postdoc at Texas Institute of Computational Mechanics in Austin, and as a research scientist in Lockheed Missiles and Space Company, he moved to the University of Oklahoma at Norman as assistant and later on as associate professor. In 1980, he was offered the full professorship in engineering science and mechanics at Virginia Polytechnic Institute and State University. And in 1986, he was appointed as Clifton C. Gorvin Professor in the same department and university. Since 1992, he owned the Oscar S. Wyatt Jr. Endowed Chair of Engineering Mechanics at Texas A&M at College Station. In 1998, he was appointed as Distinguished Professor, and since 2010, he's Regent Professor in that university. Today, he owns the O'Donnell Foundation Endowed Chair at the Center of Innovation and Mechanics for Design and Manufacturing in Texas A&M. He has been also honorary or distinguished visiting professor in many other universities in North and South America, Asia, Oceania, and Europe. In our country, he has occupied the Chair of Excellence at the University Carlos III in Madrid. Mechanics is the oldest of engineering science. It was at the basis of the first industrial revolution, which changed our way of living, reduced inequalities, and promoted the most important period of progress in human history. Today, after the second, third, and fourth revolution of energy, electronics, and communication, and data and information, many people look at mechanics as an out-of-date, as an out-of-fashion discipline, with little new to offer in comparison with the trendy topics of artificial intelligence, nanotechnology, or biology. However, mechanics is at the very roots of most of these subjects, from quantum mechanics that permits the design of new materials with unseen properties, to mechanobiology that has changed our understanding of the interaction between cells and their microenvironment and is partially responsible of mechanically induced epigenetic changes in processes like tumor evolution. It also permits the understanding and control of the forces of wind, sea waves, and tidals to produce energy, prevent catastrophes, or maintain our coastal environment. As any other science today, mechanics is therefore interdisciplinary, but it is as alive as has ever been. This has been precisely the area in which the research of our new academician has been focused, from the fundamentals of solid and fluid mechanics to their applications into a broad range of problems, including composite structures, heat transfer, computational fluid dynamics, or biology and medicine, among others. For the sake of saving time, I'll mention only some of his main contributions, like the development of polar and non-local continuum theories, plastic and viscoplastic models for metals, new mixed and penalty variational formulations, and models for solid and non-Newtonian fluids, or damage and fracture theories for the lamination of composite and other materials. Especially remarkable is his work on the theory of plates and shells and laminated composites that have been implemented in commercial final and computer programs like Abacus, NISA, or HyperExtrude that are used worldwide. The impact of his research is overwhelming. more than 900 papers, 21 books with several second, third, and fourth editions, with more than 48,000 citations and an H index of 98 in Scopus. Dr. Reddy has delivered over 170 plenary, keynote, and invited lectures and international conferences, and supervised more than 70 PhDs and about 50 postdoctoral fellows and research visitors. JN Reddy is the editor-in-chief of 3 international journals and member of the editorial boards of 24 leading scientific journals in the field. Since 2000, he's highly cited researcher, and he is in the top 100 of ISI highly cited researchers in engineering. He occupies the 5th position in mechanical engineering and the 13th among all engineering researchers in the world, 9th in the USA, in the ranking of scientists published by the Stanford University. Finally, Professor Reddy is Life Fellow of the American Society of Mechanical Engineers, of the American Society of Civil Engineers, where he was member of its executive committee and chair of the Applied Mechanics Division. He's also founding member of the U.S. Association of Computational Mechanics, where he was former president and member of the International Association of Computational Mechanics. Moreover, he's member of the American Institute of Aeronautics and Astronautics, of the American Society for Composites, of the Institution of Structural Engineers of Singapore, of the Aeronautical Society of India, and the Institution of Structural Engineers of the United Kingdom. The enormous work in research, teaching, and technology transfer of Professor Reddy has been recognized by multiple awards. Stand out, there are 10 doctorates honoris causa in universities in Asia and Europe, and the most important prizes of research world in mechanical and civil engineering. Again, I can mention here only a few of the many distinctions he has received, like the Nathan M. Newmark Medal, the Theodore von Karman Medal, and the SME Medal, the most important awards of the American Society of Mechanical Engineers, both in solid and fluid mechanics. The Walter L. Hoover Civil Engineering Research Prize and the Raymond D. Mindlin Medal of the American Society of Civil Engineers, the Velichko Medal and the John von Neumann Medal of the U.S. Association for Computational Mechanics, and the Olga C. Sienkiewicz Award of the International Association of Computational Mechanics, also the most important recognitions of these societies. As we shall see in a moment, Professor Reddy is also a recognized teacher, as proved, for example, by the Archie Hingdon Distinguished Educator Award of the American Society of Engineering Education, one among many others. Finally, Professor Reddy has been elected member of the U.S. National Academy of Engineering and is Foreign Fellow of the Indian National Academy of Engineering, the Canadian Academy of Engineering, the Brazilian National Academy of Engineering, and 4 more out of including ours today. If a scientist is someone who unreveals hidden laws of nature, and an engineer someone who uses them wisely to solve problems, to design new products and processes that improve our quality of life and sustainability of our planet, Professor Reddy has proven himself to be one of the best in both aspects. But even more important, like most geniuses, Professor Reddy is an affordable person, generous, close, and always ready to help as his students and colleagues, many of them in Spain or Spaniards in the US, can testify. We are completely sure that his appointment as new corresponding member of our Academy will enlarge the existing professional and personal relations between him and several of our members, will improve the links in science and engineering between the US and Spain, and will contribute to the better knowledge and recognition of our Academy. It is therefore a privilege and an honor for the Royal Academy of Engineering Spain to receive Professor J.N. Reddy as corresponding member, and I hope that from now on he will consider this building and what it represents as his own. Be very welcome.
Well, so I don't know what to say, but dear fellow academicians, and especially Professor Doblare was so creative in coming up with this. So I was sitting there listening. Is this really me that he's describing here? But I think it shows the friendship, and even I use the word affection that you showed me for in describing all the things that I have done, at least part of it. And I feel very, very honored to be here and getting personally inducted into this academy. This never has happened. First time in my life. I have been inducted with group, but this is a personal, very, very distinction that I feel very happy and proud of. So I will, as part of this, give a little bit of my own personal, what we call retrospective in going through what I've done. Not everything, in a short period I cannot, but a little bit. So please bear with me as I show some of my, I guess, adventures along the, okay? All right, let me see. Okay, so it's a little bit, you have to forgive me in putting all the medals there. But one of them that I showed, I'm yet to get, is the, by the way, this doesn't show on the map, is the one that I'm going to receive in July. This is called Gauss-Newton Medal of the International Association of Competition Mechanics that I will be receiving in July of this year, 2023. I was supposed to have received in July of this year, but it was a virtual meeting held in Japan. So, and they said, no, you deserve much better. We want to give you in person. So that's going to happen this year. So I'm very proud of and feel good about the recognition coming from my peers. That is the most important thing. Not that I got it, but being accepted by fellow researchers. So today I will be speaking of several things. First I will say a few words about myself, not so much about my family, but a little bit. Then I will make some remarks on teaching and mentorship. So most people know me for research, but I always felt at heart, as a researcher, I should be also excellent teacher and mentor to young students and faculty. So that I have done with considerable passion. I've used that word because I really, and that is what keeps me going and feel young at heart, really. So, and then I will say again some views on mechanics, and Professor Doblare was right in saying that everything that we do in engineering, all walks of engineering, is mechanics. Mechanics is the fundamentals of everything that we want to study. And those who think that mechanics is dead, they're dead wrong. Okay? So mechanics is really moving the frontiers of science. I use that word science because mechanics is indeed science, fundamental understanding. So I'll say a few words about those. Then my research over the years, I will just give a glimpse of it. I won't go into detail. But then I will talk about three topics: shell finite elements, and then non-local mechanics, that is my most current research, and then related to that is a graph-based finite element analysis for damage and fracture. So this is a very new, I would, again, please forgive me if I say in a way that I'm expressing egoistically. That's not the issue. I want to really tell you how excited I am about my research. So this is, I think, is a paradigm change. And I'll say, and So this, in the near future, I want to see that available to the rest of the world through abacus-like codes, because I want other people to utilize it and predict fracture, okay? And its propagation, not just only, one single crack, but it could be multiple cracks branching out, how ultimately it fails a component. And then I'll make some concluding remarks. So you have to bear with me. I will not take too long, but you should tell me that only 5 minutes. Okay? All right. So, and there are a lot of things that you can visit. I did publish one with my views on teaching, professional service, and research, especially addressing the young people. And so if anyone interested, I can send a copy of that, but it's there. Okay, so, and whether you believe it or not, that was my picture when I was a young boy, raised on a farm, coming from a low middle income family, meaning that we have food on the table, but no money in the bank. Okay. All right. So we had to depend. My father only prayed for the rains. Water is a big issue in India. So I used to help my father with, going to the farm and spreading the organic fertilizer. Organic means it is all the thrown outs, compiled over a period of several months, and we take that to the field and spread it. So it is no artificial, no chemicals. It's a very natural fertilizer. So my mother, I do remember her, but I don't have a picture of her. I mean, in those days nobody takes picture. So she died of breast cancer when I was actually 10 and a half or so. So, but I had, just like in Spain, in India, the culture is such that, my mother's sister would take care of me. So I moved into a city where she was living, and that is where I started going to primary, middle school, and high school, and so on. So then, those days, the engineering was 5-year integrated course. In fact, I was the last batch of that. After that, it became 4 years, which is common everywhere. So I came to USA in 1969, January, I remember. That is the same year landing on moon took place. So I remember vividly watching that, sitting in the, in front of the TV. So then I was very fortunate to find, so let me go back. So that is Professor J.T. Oden, who is now at the University of Texas. Actually, almost all of my dissertation work was done at UT Austin, because when I joined him, he moved to UT Austin. So I moved with him, but I had to get degree from Alabama because I finished my coursework. Okay. So then my wife joined a year later. I put the word Aruna means it is the morning sun's color. So that is why I put a little bit of color there. Okay. So I won't say too much about her, but I have to say I am so passionately involved with my work. Without her help, I wouldn't be doing that focus. So many times people wonder why we don't talk about our spouses, but they are the best background support that I have received and continue to receive. All right. So continuing that, I joined as a faculty member. I worked only short period at Lockheed. I was really impressed. He did so much research to put all those things in there. I don't think I said all those things anywhere, but it looks like he found everything, composed it. So what happened is I was really interested in academic job. This in 70s, it was not a very good time in all over the world. Jobs were very difficult. And so I applied, I even have today a bounded copy of all my letters to different institutions, memory. And when I go look at it, many of those people I know them very closely now. So all of those are rejection letters. Yeah, they're saying that we don't have a job. If we have one, not only we give a job, but as an associate professor, not assistant. Because I already published a couple of books with Dr. Roden, and so the things were not very well. So then I applied to industry. So very first job I got is Lockheed. So I was there 6 months. Then I get interviewed to appear for the faculty position at Oklahoma. So Professor Charlie Burt, that is shown with me in the picture, he was the director of the School of Aerospace and Mechanical Engineering. So, and he's very well known in composites research. So that is how I got into composites. See, before that I was doing Hilbert spaces, Sobolev spaces, convergence and existence of solutions, very mathematical. Okay, that is what Dr. Roden was into those days. So when I got there, then I realized we cannot be engineers talking about Sobolev and Hilbert spaces. We have to do something that actually is impactful, societally impactful. I'm not saying mathematicians are not, but engineers come close to the societally impactful work. So I decided to embark on a journey into composites. So that's really happened during that period, and was recognized with the different kinds of awards, local means institutional awards. So then I moved in 1980 to Virginia Tech. So everywhere I've been there, I was really taken care very well. People liked me, they valued me, but yet I moved only because I wanted to go to a better program in mechanics. And Virginia Tech has a Department of Engineering, Science and Mechanics. So, and it was very well known, and so I was there recruited in 1980. I only applied as an associate professor, but they made sure that I accepted. They gave me full professor. So this is again, I'm very pleased to share that with you, but I mean, I was only, in 5 years I became full professor, okay? So 75 and 80. And then in 92, in a nationwide search for an endowed chair, I was recruited as the first holder of that Oscar White chair. And so I'm still very active, as you know. And so I want to say that I was very fortunate to have a teacher and mentor in Professor Oden. He's a very southern gentleman, and he, by the way, the institute that he established at UT Austin is now named as Oden Institute. So from that, so I just saw him. I went to a picnic he organizes every year in April, so I was there to see him. So, but he's, many, just like our own children, if you tell them, they will do exactly the opposite. If you tell them. But if you don't tell, but they observe you and follow. Okay? And that's exactly what happens even in teacher-student relationship. So if you say things that in a way that you're telling them, that feeling is not very well taken. But if you only tell them in a way that you're advising, then they will take it differently. So, but it gave me the good background and also passion for teaching and investigating research. Okay, so that is the end of my personal thing. So remarks on teaching. I think I said many times, but I learned a lot by teaching. But simply because I had to stand on my feet and confidently explain unambiguously concepts, difficult ones especially. That means I have to prepare. I have to know first hand myself before I can explain to somebody. So that made me much more stronger in understanding everything that we do. So it's not like I just go into the classroom while cleaning the board, I will think of what do I do today. That's not the case. I prepare. And that's how my books came out. And many people ask me even today, most common question they ask, how did you do so many papers and books? So I always joke that I have a twin brother who works in the basement. And Texas has no basement. But I think it is when you have so much passion and interest to explain things and teach well, the material you generate, it naturally becomes a book because people say this is very well done. So when I wrote my book on my own, first one, Finite Elements, I never thought I would publish it because people like Odin, Zinkiewicz, all these people famous, I never thought that. But their books were not at all useful to teach from. So when I did that, so one day Professor Odin visited me at Oklahoma. He asked, typically like a parent, what are you doing in research? What are you doing in teaching? So I showed him these notes. Then he said, JN, you should publish this. So I said, oh no, not like it's such a young person, Zinkiewicz book. No, this has a different, reason to be published. And I still waited until I moved to Virginia Tech, I did not publish. But that is my most popular textbook. Second one is Composites. These two books are really very well taken. But I enjoy working with the young people. This is another thing that we all agree. They bring a lot of energy to us. Every time they come and go, right? But every time you see very young people, and they create such a excitement in anything that you do. Of course, there are always, just like raising kids, you will have headaches, but I always want to look at the positive side of our profession. In fact, there is no other profession that has this impact, influence on the minds of young people, especially professionally. I mean, I'm sure the school teachers have more impact than we do, because that is the formation years. But to set them in the right direction in terms of where they end up, we have ample opportunity. So that is exactly what I feel proud of. So we never should think, but it is a responsibility, not just a job. Well, I don't want to give a lecture but we really take a lot of pleasure in helping these by being interested in their learning. And that's what I do. So that really makes me very, popular, recognized teacher because I care about them. So, and we also should be good mentors. It's not just only teaching the tools of your profession, but you should care about their future. You prepare them in a way they can handle when they get to the job. Okay, so mechanics, I said a few words in the beginning. I will say that everything we do as engineers is model. Model means represent what we understand either through experiments or observations, how to quantify, right, differential equations, and using the laws of physics. So at the end of the day, these equations need to be solved, and that's where the computational mechanics comes in. But one thing that I, especially in the last 10 or 15 years, I've been telling people, everything that is in the books is a model. See, what a lot of young people think that we have to solve those equations exactly. I tell them it's not exact model, first of all. There is no exact model in reality. Because everything that we develop is based on assumptions. And those assumptions can get better as we understand better. We kind of take to next level, but we never get there. Because there is no such thing as exact in the real world. Okay? So we can only improve on what we know. And just like Newton said, by standing on the shoulders of the joints, you can see further or farther. And that's exactly what research is all about. All that work done by the people before and people during college, we expand on it, that improve on it. Mathematical models, computational models, so that is really. So only two things matter, especially in engineering. One is the functionality, that is, what is the probability of failure of that component, okay, system, okay, in a broader sense. And second is the cost. So we don't teach too much about cost in the, even though there is a course on economics, required course in engineering at undergraduate level. But cost is very important thing ultimately, because you have a balance between the two. The reliability of the product and cost of the product. And this balance comes by the application. Where do you? If it is a medical prosthetic, we put more emphasis on number one. We want it to be more reliable, even if it costs more. But if it is some infrastructure, like asphalt on the road, yeah, we can take some chances, making it cheaper. If it creates a pothole, we know how to fill it up, right? So this is really a very important part of our engineering. So this slide is very important for me to give the message. No matter what you do with any new method that you come up with, end of the day, you are really trying to create a system of algebraic equations for the mathematical model that you derive, okay? So let me start with, the first picture is really discretization of a domain with finite elements. It could be triangles, quadrilateral. Second one is known as a meshless method. So meshless method, Ted Belichko, some of you heard of him. He was a kind of advancing this. When he was living, unfortunately died 4 or 5 years ago before COVID of a massive heart attack. But he was promoting that, but unfortunately it is not a very, efficient, in a broader word. Efficient means costing less, but giving more accuracy. It was not. But only because he was there. A lot of people got on that bandwagon, and a lot of papers came out of, especially China. Even today. So, but it totally died. Once he died, Ted Belichko is gone, because it's not a very practical method that could get into abacus, of course. And then there is this finite volume technique. So the two techniques that are most popular today are finite elements and then finite volume. So these two, all of them share one thing common, is just bunch of nodes or mesh points. So what we determine, independent of the physics, we determine the values of the significant quantities of that physics at selective mesh points. And these we call duality pairs. So nature has a duality, means cause and effect. So, and there could be multiple duality pairs in reality, because everything that we do in real world, unlike in a classroom, is multidisciplinary. Okay, so it's not one physics, it's really a lot of heat transfer, fluid mechanics, solid mechanics, electromagnetics, all of those are there. So the question is, what is the degree to which we want to investigate a particular phenomena? Depends on your goal of application. And that's where you decide to do only stress analysis or only fluid flow, right? So, but all of them are endowed with the duality, cause and effect. So there are multiple pairs of duality. Okay, so you can have temperature and heat, one duality pair. Then you have force and displacement, another duality pair. But what is important is the duality is unique. There is no, I would use lack of other word, no polygamy. Means one dual variable is only dual to one other. It's not dual to others. Okay, that's exact. So force is not dual to temperature. Okay, so that's very important. So everything that we do in all the numerical methods, end of the day, is to relate space through algebraic equations. All these numerical methods convert the differential equations into set of algebraic equations. Okay? All right. So, and then rest of this is very standard. So my research has really started when I was a PhD student with Dr. Odin on primal dual variational principles. So my PhD was largely theoretical. Okay, that means come up with what are the variational principles of engineering physics, including electromagnetics, everything. So we came up with 7 primal dual variational principles, and many of them led to mixed variational finite elements and so on. So when I joined Lockheed, the first project they gave me to study hypervelocity impact on. So that really gave me very good background and experience with real world. So, and then when I joined Oklahoma, I had a collaboration with the geology department. So formation of salt domes and tectonophysics. So finite elements was a very good tool to study. Of course, the phenomena, it's a matter of scale. The spatial scales are large, right? And then I also, with Dr. Charlie Bird, doing composites, bimodular materials, meaning they have different constitutive behavior in tension compared to in compression. So this is, by the way, not commonly seen in many cases, but it is there. Think about tire, reinforced tires, like Kevlar. So they don't behave same way in tension and compression. So the modulus is totally different. Well, in fact, even rock, it is very, very difficult to, in tension they are easy to fail, but in compression it takes a lot more force. Okay? So that's a very simplest example. So that is another, so naturally it is a nonlinear problem. So we have studied that. Then I got into this shear deformation because Charlie Bird kept saying that the shear interlaminar stresses between layers are very important because they are very strong, the laminates in plane, but when you bend, there is a tendency for them to delaminate. So how do we represent the state of stress between layers? And that is when I got into the third order shear deformation theory. And that is the most cited paper to date in my research. So, but most important satisfaction I have is not because of citations. Now I know these days everybody talks about citations, impact factor, all that. But how useful it is to, so the usefulness can come 2 ways. Societally impactful, nobody has to cite it, but it is doing something, improving something for society, whether it's a communication, transportation, whatever it is. The second, helping other people to expand their horizons. Okay, so that means this topic, a lot of people got onto this and they expanded in terms of, higher order or applications. So, and today I think that is considered to be the optimal order theory. If you go to higher order, some people tried it, you get more variables but not much accuracy. The gain is not consistent with the expense. Okay, so I also did penalty finite elements. At that time, it was viscous incompressible flows. The mass conservation is a constraint because the same unknown velocity field appears in the conservation of mass equation. So it is considered as a constraint. And it was showing very strange results if you go blindly construct finite element model. And the pressure was coming to be very erroneous, totally. So that is when I got into that. So I have to say we were able to fix the pressure variable by eliminating it and computing it in a post computation. So that is what I did in penalty. And this ended up in that NISA commercial computer program. And then this relationship between classical and shear deformation theories another topic that I worked for a short period, but it was, so I want only thing that I want to say here is, suppose you have a analytical solution to a classical beam, plate or shell theory, okay, using whatever method. Then we develop relations that immediately can extend to any higher order theory only algebraically. It will relate displacement of higher order theory in terms of the lower order theory. It's just algebraic relation. You don't need to do any more work. So I think it is very, very interesting at least. And then I've been working for most of my life on shear deformation theory. So this topic is very, even today, very important because all of the shell elements in commercial courts are based on some gimmicks or fixes. One of the fixes is the reduced integration, but it can create side effect. So this is like in real world when you take medication for a health problem, and even though it is tested with a lot of mice, animals, this and that, or they might have even tested with 1,000 people, but we are very unique, each individual, right? So the side effects can never be totally understood. So the side effect of this, all the fixes in technical fixes can have side effects. That means it seems to fix that problem, but it may lead to non-conservation of energy or localization which are non-physical. So that is why I want to get rid of that, and that's what I did. I may say a few words later. Then last one is least squares. This is a finite element formulation fluid dynamics. So if any of you know a little bit about fluid dynamics, it is not same as structural mechanics in terms of minimization aspect. There is no principle of virtual work. Doesn't apply. So you don't have minimum or total potential energy principle. None of those are available. So when you take blindly FEM, so-called integral statement, and apply to fluid flow, they don't work very well. So because there is no concept of minimization. And so we have come up with the least squares technique that is very, because it has nothing to do with the physical principle. It's a minimization of a quadratic functional, which we can construct for any problem. And the latest fashion is non-classical continuum theories. So this non-classical, as the word suggests, is whatever we put into the classical continuum mechanics is limited by assumptions. It's not by principle. Physical principles are general statements. Okay, the time rate of change of internal energy is equal to sum of the forces. That is the second law of Newton, right? So, but the thing is, how do you write that in the form of an analytical expression? At the time of writing it, you make assumptions. That is where the limitations come. So the classical continuum mechanics does not allow a point to rotate. Point to move, it can translate. So this rotation, local rotation, is one of the things that is helpful to include, and that's what we have done in this. Okay? So there are many other things, but all of these have those four elements. Everything that I've done somehow connected to finite element analysis, shear deformation theories, variation principles, and continuum mechanics. Okay, so I've written a lot of books only because I was teaching at the same time, and all of the books I've written, by the way, there is a latest one, I did not put one here, it just came last month. But sole purpose of writing these books has been to facilitate learning. Actually, that is where I started, and they ended up being in the books. So I always included the most relevant research ideas that can be brought into the textbooks as a extension of what is already known. So that's one of the things that I've done. So this is my other famous book. So So this is the book where I have the two theories that are typically referred in my name in the literature. In fact, there are many, many papers. The title of the paper has Reddy plate theory, and then go on to say what they did with it. So again, I don't want you to think that I'm saying egoistically, but I feel good about something that people used it and enlarged or expanded and advanced the field. So the first one is this third order shear deformation theory, where a typical straight line does not have to remain straight line, and it doesn't in reality. So, but the degree to which it becomes a curve is, of course, you can debate it, but the real issue is to bring the shear related stress field, which is very important for interlaminar stress. The other one is the so-called layer-wise theory. So that means, when you create this laminate, each layer has the ability to slip past the other, ability, if you let it go. If you don't let it go, then they create stresses, right? And that is what we are trying to determine. And those are the interlaminar stresses. And so these theories are so-called single layer theories. That means the identity of layers is lost because you homogenize it. Whereas here you have the identity of layers. Okay? So this is really close to 3D elasticity. So I've done all of that. So by the way, the latest I checked, it has 50 citations. So it's not a correction to yours, but you got the data about my citation. Now it's not 50,000, it is 97,000. Okay, and my H index is 113, not 70 or something. Yeah, well, so this tells me something. And I want especially all of you, I look at you younger than me, okay? So Antonio, we can be thinking more, word young means at heart, okay? So when I mention this impact factor or citations, see, they come in later years because the work it takes time for people to recognize usefulness. So my citations increase much more rapidly, and my H index much more rapidly in the last 10 years. I mean, I was surprised why this is happening, but so people should have patience. Okay? All right. So those three things I wanted to say, I will say it very quickly. So what I have done in the case of shell, so I told you that shell element in commercial codes has still limitations and side effects never understood. So what we want to do is create a shell element that is free of these things. So what we did is two things. One, we don't do any reduced integration. It's a very organically developed element. Organical means I don't do any personal things to fix. So let whatever the formulation says I have to use. So second, I allow the thickness of the shell to change. So think of the shell here. This would be, by the way, layered shell. So when you think of a cylinder and internally pressurized, it is going to change its size, right? So where is the material coming to become larger? It has to flow from the thickness, right? Think of a balloon. When you blow out the balloon, when you start a balloon is only a few inches, right? And looks very dark rubber. But when you blow it out, it becomes big and you can see this transparency. How did that happen? Because the thickness of the balloon is changed to almost zero. Okay, I mean engineering sense, it's not zero. But if you put more pressure, the thickness cannot take it anymore. It bursts, right? So we don't have same level of blowing of this, but when it large deformation, the shell has to expand. And that expansion makes the thickness to change. And none of the commercial codes allow that, because the shell theories are not built on that. So we brought that element. So we added additional degree of freedom. Oh, sometimes it looked like it. Okay. doesn't, but sometimes it looks like there is a, you see that little bit? So this is the 3 displacement, 3 rotations, and then 7th degree of freedom is the stretch. Okay? So even if it doesn't stretch much, okay, I'm being a little bit technical here, you have to let it do whatever it needs to, instead of saying, oh, you don't stretch. You don't stretch means you are intentionally making thickness direction infinitely rigid. That is the problem. It's not so much, oh, it's stretching so much. Leave it alone, let it stretch whatever it needs to be. Okay? So we, I don't know if it will work. Let's see. I think I need that. Okay. This is one of those. Okay, let's see. How do I get to the? Where did the mouse go? The mouse. Can we put the mouse? Sometimes with all these technologies, you go somewhere, it works there, please. We don't need this, right? Sometimes it takes a little bit of well, it looks like, let's see. Yeah, I think some reason, it works, and sometimes when you connect to a projector, they don't work. Okay, anyway, just to make sure that, so this is one of those examples where you pressurize the cylinder and it blows up. The animation would have shown that. Okay, so anyway, since the animation are working, I'm going to show the next slide. So here I show the state of stress due to the internally pressurized, and we can convert the pressure into a load parameter, P, and you plot the P versus the stress state. So I want you to see several important things here. Abacus and ANSYS shell elements, they predict this result. They match very good between them, right? So then you go to same abacus and ANSYS, I use the 3D finite elements. Okay, so I have to tell you, if it is a shell element, it doesn't allow the thickness stretch, because they don't have it. Whereas 3D elements are, they can do anything in any direction, right? So that is the result. So clearly shell elements are not doing good job, right? And our shell element is along with the 3D. So then you say, oh, why don't you use 3D? Why do we need shell elements? Well, so I just want to show our shell element. By the way, this range here is really maybe out of even shell assumption. Okay, but in a long way they are very close to each other, right? Okay. In fact, ANSYS and abacus don't agree with each other either, with the 3D. So the reason is it only takes 66 CPU units corresponding to nearly 6500 by the ANSYS, whereas 720. 1 order of magnitude compared to abacus, 2 orders of magnitude compared to ANSYS. So that's a lot of saving. So it justifies using shell element or 3D elements when you can get the same level of accuracy. Okay, so that is the end of that. The second topic is this non-local mechanics I'm using in here a different way. Okay, so let me explain a little bit. So if I have to build finite element for this, I can treat it as each ligament as a frame element, right? 6 degrees of freedom, 3 displacements and 3 rotations. And then you have millions of these ligaments. So it becomes practically impossible to use every ligament of the architecture as a frame element. So what is the best? The cheapest way is to homogenize. But then you lose the local information if any of these ligaments are buckling, right? So the in-between is where we came up with this non-local concept. So suppose if you homogenize it, but not in the model. But if I come up with a theory, every point now has the ability to rotate also, which is really rotation of these ligaments, which really they do rotate during the, if you compress or something, right? They rotate and even buckle. So that is what we call micromorphic theory. So we have developed that, and so we studied. So one simple example is a sandwich structure with I-beam. So a typical unit cell looks like this. So what we do, we use 3D shell elements to get the unit cell information, which is very standard. Then we use a theory that is two-dimensional, plate theory, but I bring these two rotations, okay? And so how do I connect this information I learned from 3D to this? Energetically, we create an equivalence and relate the stiffnesses that are required here. You all know there are ABD type stiffnesses, and they are going to come from here. It is only done numerically, you cannot write equations. Numerically, the stiffnesses are computed in such a way by equating the degrees of freedom coming from 3D to those coming from the 2D. Okay? So this is how so ultimately this ADGH are computed numerically because of the information I have, and then I have the plate theory. Okay? So it really did excellent job. So I'm going to show you, if you plot the displacement along this line, okay, this is exaggerated, just for you to see. The 3D finite elements is the blue, and whereas the 2D micropolar theory is red. So they are very close, even in and whereas the classical one is lot of error. You can see anywhere 15-20% easily. Okay. So we have done that for buckling as well, bending. By the way, if we change the thickness of the webs, and as you change it from very thin to thick, our results still match with 3D. Okay? And whereas the classical theory error increases even. Okay? And we have shown the error plot in here itself. So you cannot see there is any error at all, almost zero, unless you blow it out. Okay? But then it is very small percentage of like less than 1%. So we have also done for buckling, uniaxial buckling, biaxial buckling. So what you are seeing is the 3D finite elements and micropolar theories are essentially the same. Okay? So whereas the classical theories are very much in error, especially if you go to higher order modes. Okay, the last topic is fracture. So I hope you're all, getting tired of listening to me so much of this. But see, there are two kinds of fracture models in engineering. One based on continuum models, so like linear elastic fracture mechanics, cohesive zone model, extended finite element method, continuum damage. That's one. There is a second one called bond breakage. So that means somehow create a bond between points. Remember that picture I showed about the continuum, all numerically you have points, right? Between any 2 points there is a bond. Bond could be a force or strain, field, whatever. So you declare when that exceeds some allowable. Say it failed, right? So the problem is this can be only used for a bond breakage model where it doesn't have continuum assumptions. Whereas this doesn't have the bond breakage. So then we thought, why don't we come up with a continuum theory that has a bond, meaning 2 points share certain force bond between them. So that is what we have done, and it also should be good for many cracks, not single crack. In fact, all those continuum damage models are good only for single or 2 cracks or 3 cracks at the most. And not only that, you have to know which way they might be going, so that you lay your mesh. And that means you already know half of the solution. And in real world, you don't know that, because the load path dictates, and also geometry dictates the actual growth, which way it is going to grow. So if you don't know that, then you don't have the ability to mesh it correctly. So whereas our method is very generic. So can we have the best of the both? And that the answer is yes. And so we developed using no new finite elements. The same order finite elements, except we look at the finite element, for example, a triangular element, as one that is connected by 3 points. So I don't look at inside. Okay? So we converted the strain energy in terms of the strains or forces along the edges. And then I can use bond breakage models. So I use continuum mechanics to develop the finite elements. But then I created this bond, and what is the interesting is these bonds are connected. See, several elements. So if I draw a circle, you see that one edge. But that one edge is related to all the neighbors, right? So it becomes now local. Okay? So, and we also brought probability of failure into the picture. These are the probability functions. So an original K matrix is now changed to this little bit complicated looking, but the minute you make this diagonal, it degenerates back to the classical finite elements. So we were able to, unfortunately our videos are not working. So this is a real experiment, okay? And this is the finite element, our thing. So it predicts exactly this, okay? So because I cannot think that it will go like this. So if you put a mesh, and these people extended finite elements, really it did not converge even. Okay? And it predicted wrong results, and whereas ours was published in 2019, and we continue, and this year we published in Royal Society Proceedings paper on this. So here is a concrete block. It's fixed here, we push it here, initiates damage here, and it propagates very nicely. So these are the kinds of tests we have done, and so we also, so for example, this is another very good example. Abacus, the extended FEM or cohesive zone model, it initiates, it goes and it gets stuck. It doesn't know what to do. Whereas in our case, it delaminates because this is a hard fiber. So our physics is such that it does not go and what you call stalling of the process. It actually finds weakest direction and goes around it, delamination. So, all right, I want to just say, how did you write so many books? And here it is. So I said this before, right? Okay. But seriously, I have benefited enormously by working with my students, postdocs, and colleagues. Some of you are in the audience here. I really feel my job is to give ideas, facilitate their, contribution to a common goal of advancing the science and technology. So there are so many of them, and all these citations, impact factor is because of that, not just because of me as a person. It's really the contribution. So papers that I have written with a lot of people all over the globe, including Spain, okay, Portugal, and Finland, Germany, Italy, and then India, little bit with China, but mostly with through Hong Kong. I don't work with China for one single reason. United States is very, very negative. So every time I write a paper that they see a Chinese person, they ask, are you really collaborating? Are they paying you money? No? So I said, okay, I probably don't get to that side, right? So that's why I say it is dedicated to my students and colleagues who have worked with me for years, and without their collaboration, it would not be possible to stand here and give this
Your head.
Oh, okay, I have to stay there.
With the glasses. Be careful.
Yeah,
Take
it's
out
okay.
the glasses.
Yeah. Thank you again. So maybe we can have a group picture?
Sure. Yeah, of course. No.
Oh, I have one more thing.
This is a print
Yeah, we'll put it there.
later.
Yeah.
And You keep this for this. You have in this case, no?
Yeah. Thank you.
You can
Oh. So we